today's tutorial. And in last week, we have already started a little bit about the soil slope with the soil nail installed, right? And we actually didn't discuss the example for this lecture. So we started with example 1. Okay, you can read the question for 2 minutes and we start later. All right, let's see this example together. A 45-degree slope is excavated to a depth of 8 meters in a deep layer of saturated clay of unit weight of this value. Okay, a deep layer. A deep layer means this stratum can be the depth of this stratum can be very large. Okay, but no exact value is given in the example. The relevant shear strength parameter Cu is equal to 65 kilonewton per square meter, okay, kPa, 65 kPa, and phi u is equal to 0. So here actually tell us this example requires us to analyze in terms of the total stress approach, right? Total stress approach, because the phi u is equal to 0, and determine the factor of safety for the trial failure surface specified in the left figure. A trial failure surface, because this one, ABC, this curve is just a trial curve. We need to use the grid searching method. Okay, for example, we have other different rotation center point, not only one O, okay? And with respect to one rotation center, we can specify different failure surface, okay? So here actually just shows us one example for the one step in the grid searching method, okay? And this ABC is specified in this example. So we can use the trigonometric function method to determine all the values below. For example, the area of ABCD, this one, ABCD. So the moving soil mass, some area of this irregular shape. Okay, how to determine it? Because we know the angle here is 89.5 degree for the angle AOC, right? And we will assume that the ABC actually is a curve from one circle, right? The R here, the OC is equal to OA, also equal to OB, right? So if we know the angle AOC 89.5 degree, we actually can calculate the area of the OABC, because this is one part of the circle, right? And this one, we know it, and we can calculate the area for this triangle, the green part triangle, because we know everything actually. We know the angle here. We know the this one, the OC length, and we know the height 3.5 meter, and this one is perpendicular. So we can determine this angle and this angle, right? Then we can know the length of this side. So we can calculate the area for this triangle. Similarly, we can calculate the, if we know this length, okay, we can directly to determine the CD length actually. If we know the CD length, we can get this length. Okay, we know the height of this blue triangle, which is equal to 8 meter. So actually it's a blue triangle. The area can be also calculated using this trigonometric function, okay? So we know the area, then we use the OABC area minus 2 area of these two triangles. So we can get this cross-section area ABCD is around 17 square meter. Okay, this is not an exact value. It's around 60 meter, but we just use it. And the weight of the soil mass, we use the area multiply the unit weight, 90, which is given here, right? Of course, this weight actually is a line load, okay? It's a line load because we don't know the length, okay? Which is perpendicular to the paper, okay? We don't know the length here, but we use the line load concept here, as we discussed in the lecture. And the centroid, the rotation point, is 4.5 meter. This means this part, the resultant weight of this ABCD and the lever arm or the moment arm, okay, the distance between this resultant weight to the rotation point. The lever arm is equal to 4.5 meter, okay, from O. And the angle, we know it, and the radius, OC, okay, we know it here, and the arc length, 18.9. The same, we know the angle, we know the radius, we can know the arc length here. So actually, we will just use the limit equilibrium method using the total stress approach. And this formula we discussed in the lecture already. And the upper part, the numerator part, is the resistant moment. And the bottom, the denominator part, is the driven moment, right? CLA is the length, this one, multiplies R. R is the moment arm for all the shear strength, for all the shear stress to the rotation point. Okay, so we get it easily. And the W, we get it already here, the weight, and multiply the moment arm. Okay, we get this value, 2.48. The F is not necessarily the minimum factor of safety. Not necessary, because we just show you one example in the grid searching method. So with this same condition, we have already discussed about the Taylor's method. Taylor's method is one design chart for total stress approach, right? So for this question, for this example, the angle, the slope angle here, the beta is equal to 45 degrees. We already know it. And because this is a deep layer of saturated clay, right? Just as I just mentioned. So this D value, okay, this D value, we can say it is approach to infinite large. Okay, we just assume that because it is a deep layer. So if we use this design chart, when beta is equal to 45 degree here, and we draw a vertical line, vertical straight line, okay, then touch this line, because this line represents the D is equal to an infinite large value. Okay, so we can get the NS based on this design chart is equal to 0.18. Then directly to input all the parameters. Cu, okay, 65, gamma, H, the height of this slope. So we can calculate the F, the minimum factor of safety. Okay, this F is a minimum. Minimum factor of safety based on Taylor's method is equal to 2.37. So you can compare 2.37 and the 2.48, right? And the 2.37 is smaller. So just based on this simple comparison, we can see that Taylor's method actually provide us a smaller factor of safety. Okay, the minimum factor of safety based on this method. Okay, so this just show you the comparison between the calculation and the directly using of the design chart method. This is Taylor's method. Of course, we discussed some better method in terms of the effective stress approach, okay, proposed by Morgenstern, right? Bishop and Morgenstern later, right? This one actually concerns about the importance of the friction angle, right? The friction angle. And it will use the effective cohesion here, right? The C prime, rather than only assume phi is equal to 0. Okay, let's see this example 2. You can go through this example first for 8 minutes, okay? And I will show you an Excel file to show you all the details of the calculation. All right, let's see this example together. And using the Frillenius method or Swedish method and Bischoff method of slices determines the factor of safety in terms of effective stress. Okay, the phi is no longer equal to 0 here of the slope shown below for the given failure surface. Using peak strength parameter, C prime is equal to 10 and phi prime is equal to 29 degree. And using the critical state parameter, which is equal to 31 degree, and the unit weight of the soil, both above and below gamma or gamma set, below water table, a gamma prime, okay, or gamma set is equal to 20. Okay, this is a bulk density. This is a saturated density of the soil. Okay, they are all equal to 20 kilonewton, okay, cubic meter. Okay, this is bulk density. Okay, bulk density, bulk unit weight. Okay, this is saturated unit weight. They are assumed to be equal. Okay, so in this question, actually, we can say there are two sub-questions, right? And one is ask us to use the peak strength parameter, C prime, phi prime. And another one is a critical state parameter, okay? And you see here, one is 29 degree, another one is 31 degree. Okay, if we go back to this slide, you see here, peak envelope is here, this one, which is higher than what I said before is a critical one. Okay, critical one will be lies in between, okay, of the peak curve and the residual curve, right? This is the phi CV. So as I discussed with you, phi CV will be between these two curves, but why? In this question, the phi CV is equal to 31 degree and the phi peak is equal to 29 degree, right? So actually you can see here that this value should be smaller than phi max or phi peak, right? Okay, so you may ask me this question. So I will give you some explanation here, okay, about this confusion actually. Why the phi peak will be smaller than phi CV prime? Okay, this is possible. This is possible, but this is not absolutely correct for all the soil, of course. This is possible. Why? Because this curve is a straight line. This line is just a straight line, which is just a simple curve fitting. Simple curve fitting. Okay, so for the critical point, for the critical friction angle, we assume that it must surpass the original point, which means for determining this value, this C prime must be equal to 0. Okay, so we will have one point absolutely at this original point, and then to draw another line, a straight line, okay, with a slope, and this angle is equal to phi CV prime. Okay, this is what we do for the critical curve. And for the peak curve, we also just use this simple curve fitting method. For example, one point is here, one point is here, one point here. We draw a best fitting straight line to fit these three points. Then we will have an interception value for the cohesion, C prime here. Okay, so we will have some value of C prime. So let's draw another maybe a little bit extreme case. Okay, for this three point, okay, we have a best fitting line here, and the C prime is equal to 10 kPa. Okay, so because we have an interception, okay, we allow it has an interception value, C prime. So now the curve one, okay, or curve peak, the angle will be possibly smaller than this phi CV prime. Okay, you see, because we can allow the interception part. But for this phi CV prime, we normally just restrictly to fix the starting point at the original point, which means the C prime is equal to 0. Okay, so that's why based on this simple curve fitting method or straight line fitting method, we can possibly get a value of phi CV prime smaller than the phi P prime. Okay, this is just a result of curve fitting. Okay, this is my explanation why the phi CV prime is smaller than phi P prime in this question. Okay, because it's a simple curve fitting. Okay, simple curve fitting. Why we do the curve fitting? Because we can fit it with a straight line, which is more easy for us to use. Okay, this is the reason. So I will go transfer to the Excel file to show you all the details about the calculation. So I think you can see the Excel file now. Okay, I already shared the Excel file. So for the first sub question, the C, okay, here is 10 kPa. The phi is the peak friction angle, which is equal to 29 degree, right? I'm not sure why today I cannot write directly on the Excel. Okay, I use mouse. The unit weight and the tangent phi is directly calculated here. But one thing I want to remind you is in the Excel, we cannot directly to use the degree value in the tangent format, in the tangent function. Okay, this is tangent. Because in the Excel, we should transfer the degree value to a radian value first. Okay, because this tangent function only recognize the radian value. Okay, we should transfer first. You see here the 29 degree, we divided it by 180 first, then multiply pi value. So this pi actually shows you the radian value of this angle, okay, of this phi angle, radian, okay, rather than the degree. So as you can see in the question, we divide this slope into 8 slices, okay, into 8 slices. So we will, for example, here in this row, we will have 8 column, right? 8 column. Each column represent all the information for one slice. Okay, let me go back to the PowerPoint. One important thing for this one, the B, the width for each slice. The width for each slice from slice 1 to slice 7, actually, all the widths are equal to 1.5 meter. But for the A slice, obviously, the width is smaller than the width of slice 7, right? So we need to determine the width of this slice first. Okay, how to determine it? Actually, we will use a trigonometric method because I draw this green triangle here, right? Green triangle here. The height is equal to 3.15, and this radius is equal to 9.5 meter. Okay, 9.5 meter. So actually, we can calculate this length first. Okay, this length first. Then we will know, for example, this is A. Okay, this is A. This is right angle, right? So A can be determined easily from these two sides, right? R square minus 3.5 square root. Okay, this is the length of A. This is the length of A. And this is the length of A. And we have another parameter, length here, 2.5, represents this part. Okay, so A plus 2.5 is equal to, okay, 7. We have 7 widths plus the width of slice A, right? Because all 7 widths is equal to 1.5 meter. Okay, so this W8, the width of the A slice can be easily calculated because we know the A value. A value is equal to here, right? So we can get the A value here, the width of the A slice, okay? So according to my calculation, the width is equal to 0.96 meter, okay, 0.96 meter. But for the consideration of simple calculation, okay, you see, in the Excel file, we just use 1, okay? We just use 1 as the width for the slice 8. For other 7 slices, the widths are all equal to 1.5 meter. Okay, so this L, you see, this L is the distance or the length of the each slice along the shear surface. You see here, this is L, and this is also L. This is also L. They are equal, right? The upper and the bottom surface, they are equal. And how to determine this L value? You see the equation here. We know the width, the horizontal length of this slice, and divided by cosine beta. This is alpha. Okay, I will explain this alpha value to you. And to divide this cosine alpha, again, we will transfer the degree to the radian first. Okay, so how can we get this alpha value? Because we cannot write on the Excel file, so I come back to the PowerPoint. So for this one, actually we have 8 slices. The alpha value means we will draw a secant lines. through the middle point of this slice, a secant line, straight line, okay? And it will have one angle with respect to the horizontal line. Okay, this is alpha value. So similarly, for the ace, we draw a secant line and we will have another alpha value here. Okay. And here I want to remind you, for the slice one, the alpha value will be a negative value. And for 3, 4, 5, 6, 7, 8, this alpha is a positive value. Why? Because according to our definition, we always use this kind of rotation of slice. Okay. The slope here is always this is alpha, right, for this slice. And for this kind of rotation, bottom surface, this alpha, we assume it is positive. But if this slice becomes like this, then this alpha is a negative. Okay, why? Because, for example, for this slice, the weight, W, the decomposed force along the failure surface actually point from the left to right, which is actually is a resistant force to resist this soil mass from sliding. Okay, but for this slice, this alpha is positive because this weight will have a decomposed force to drive the soil mass to move. Okay, that's why the contribution are totally opposite for the weight in in this direction. One is resist, one is driven force, right? That's why this alpha will be a negative, this alpha will be positive because the contribution are different. Okay, one is resistant, one is driven. Okay, so this is my explanation. Then how to determine this alpha value? Okay, how to determine this alpha value? Normally, we will draw the geometric shape of this slope in the AutoCAD. Okay, in the AutoCAD, so then we can measure this alpha value easily. Okay, using the AutoCAD. And here, actually, we use the same method as shown in the Excel file. You see, the alpha for slice 1 is minus 10. For slice 2 is negative 1, okay? Negative 1. So here are all positive value. Okay, we actually measure it in the AutoCAD. Okay, we can get it very easily. But for you to do the calculation, all the values here in blue color, okay? In blue color, we will give to you directly in the examination, okay? We will not ask you to measure it because it's difficult, okay, in the examination. So all the value in blue color will be directly given to you, okay? So this alpha, actually, we know it all. And then with this alpha value, we can calculate this L, right? We're talking about this L. And this H actually is the height of one slice, height. The middle point from the top surface to the middle point to the bottom surface. What is the distance for this slice? We just use this one as to use it as the average height of this slice. Then with this height value, we can calculate the W, right? We have the B, the width, and multiply the height, then multiply the unit weight. We can get the weight of each slice. We can get the weight of each slice, right? So that's why we need this H value, okay? And B, we know it. Gamma is equal to 20, right? And let's see, because we are required to use the Frillenius method and Bishop method. So actually, for example, in Frillenius method, we have different items, C prime LA and W cosine alpha UL, and in the bottom, the W multiplies sine alpha. Then we need to do the summation. You see, we need to do the summation. So similarly, in the Bishop method, we have different items. So actually, for this example, as to show you as an example, you should write and calculate different items in a table format, okay, for clearance. And you can do the same thing in the assignment. Also, you can do the same thing in the examination, okay? You'd better to form one, to calculate all the parameters for all the slices in a format, okay? This is more clear. So for example, for the sine alpha, because we know the alpha value, we can calculate the sine alpha value easily. And the W multiplies sine alpha for the bottom item, you see, for this bottom item, no matter for the Frillenius method or Bishop method, we need this item, W multiplies sine alpha. Okay, and W multiplies tangent alpha, you can see we will use it here. Okay, W multiply tangent alpha, all here. Okay, we have this item. So similarly, one by one, C prime B. You see here, C prime B, C prime L, C prime L is here, this one. C prime L, because we know the L for each slice, then we should have this summation for this part, C prime LA. Okay, one by one, just list all the parameters. Firstly, W tangent phi, no problem, because we know the W already, we know the phi, of course, here, right? And you should be careful. The phi in this sub-question, phi is equal to 29 degree, okay? For the next sub-question, the phi will be changed to 31 degree, okay? And the tangent alpha, we know the alpha value, no problem. This is U, okay, the pore water pressure, because you see we need the UB and the UL, right? So for the pore water pressure, gamma W, we know it is equal to, we can use the 9.8 or 10, okay? But anyway, this U value will be given to you in all the assignment and the examination. Why? Because this ZW is difficult for you to determine. ZW means the distance from the failure surface to the water table. Okay, for example, this distance or this distance. Okay, it's difficult to determine manually. Okay, so this value will be also given to you. With the U value, we can calculate the UB and UL. Easy, right? And for this one, actually, W cosine alpha minus UL, then multiply the tangent phi is here in the Philinus method, right? Or actually, we know all value calculated already here, so we can just calculate the final result for this item, Similarly for this item, okay, quite easily. And for the Philinus method, we will calculate the top item first. The top item is composed of two parts. The first part is C prime LA or C prime L for each slice. Okay, C prime L for each slice. So we calculate the top item for each slice first, one by one here, and then do the summation. You see, do the summation. Okay, then for the bottom item, for the Philinus method, the bottom item is this one. W multiply sine alpha, then do the summation. You see, do the summation, right? So the F value from Philinus method can be directly calculated using the top item divided by the bottom item, right? Just one step, we get this final factor of safety based on Philinus method, okay? But for the Bishop method, as we said, we need to use the irritation method, right? Irritation. So here, you see, there is a 1 here for the F. Because in the Bishop method, we have one F here. You see, this is F. So we start with input F equal to 1 here to calculate, okay, the whole result for the right item, right side of this equation. We get the result F is equal to 1.583, you see? 1.483 here. Then we use this 1.483 to put again to this right-hand side F value. Then we get the whole result for the right-hand side equation. Okay, I mean, then we put this one, we get another F. This F, we get this F, 1.590. Okay, then we use this one to calculate another F value, 1.607. Okay, normally you will be required to do 3 times iteration. Okay, which will give you a quite reliable or quite stable result. Okay, these two actually, the difference is not very large. Okay, so we just do 3 times irritation. Okay, actually for each time irritation, you need to calculate all these 8 values, right? Actually, the calculation workload is quite large. Okay, if you don't have the Excel, so 3 times is good enough for determining this value. So this is my explanation about the details of this Excel file, and this Excel file will be uploaded to the Blackboard. You can easily to download it. Okay. Let me show you another Excel file. You see here, this one is the second sub-question. The phi prime is equal to 31 degree. Okay, all the detail here actually are the same. The only thing different is the tangent phi value. Here, this one will be changed to 31 rather than 29. Okay, because the phi actually is different. Because the tangent phi is here, we use 31. Okay, all the other issue or other details are the same. Okay, are the same. So let's compare. And come back to the slide. You see, if we use the peak strength parameter, because we have the C prime, we have the phi, we have the phi value, we can get a higher factor of safety compared with the critical state method, right? They are all larger, right? Even though this factor, friction angle is 31, which is larger than 29, okay? But we have this value here, which will affect the C prime L, right? So actually, if we use the peak strength parameter, okay, no matter the friction angle is larger or smaller, okay, but the final result normally will be larger. I mean, the factor of safety normally will be larger than the factor of safety we obtain using the critical state parameters. Okay, you can directly see the result comparison, okay, much larger, around 50% larger, right? So as I explained in quite detail to you last time, okay, when to use the peak parameters, when to use the residual one, okay, when to use the critical state parameters, okay? I will not repeat here because this is for different cases, okay? You should know the very detail, okay? And here actually, if we just divide this slope into 3 slices rather than 8, you will see this value becomes larger again. The fittedness is 1.8 something, but here is 1.4 something, okay? So actually it implies that if we divide in more rough slices, only 3 here, we get a higher factor of safety, which means it's not that accurate because we prefer to get a very accurate result for the factor of safety. For example, 1.48, if we divide it into 8 slices, this one is smaller, which means we can have a safer design, right? But here we have a larger value, it may have misleading result. Okay, so normally if we use software to compute, so to find the factor of safety, as I said to you, the slice will be divided into 30. Okay, this is a default setting in the common software. Okay, we will have 30, at least 30 slices for the soil slope. Okay, so you can see here, as I mentioned, we prefer to use a smaller one because this is more safer. Okay, this is quite similar in the lecture 1. Okay, if we divide the soil ground into more interlayers, sublayers, okay, we will have a more accurate result for the settlement, right? They are the same. Okay, here in the example 3, actually I may not give you the time to go through by yourself. Okay, let's see together directly. And this is translational sleep actually. It belongs to this one. Translational sleep, not effective stress. This is wrong. Okay. If we have a clay, the unit weight is here, incline angle is 12 degree, and the water table is at the surface, and the seepage is roughly parallel to the slope. It's something like this. Okay, this angle is 12 degree, and a slip has developed on a plane parallel to a surface at a depth of 5 meters. Determine the factor of safety along the slip plane using critical state parameter and the residual parameter. Okay, they are different. You see, the residual strength parameter, the phi actually is smaller than the critical state, much smaller. And for the critical state strength, because the water table is just at the surface of this slope, water table is here. Okay, as we discussed in the lecture, we directly to use this formula to calculate the factor of safety, gamma prime divided by gamma set. Okay, this one, as I said, is around 0.5. Okay, 0.5. Okay, this equation you can go refer back to the slide. So we all know all the parameter, the value actually we all know. So we can directly get this result. But if we use the residual strength parameter, the factor of safety will be smaller than 1. Okay, so which means if this slope has failed in the history, okay, in the history, we prefer to use the residual parameters as an, conservative prediction of the factor of safety for this slope, which has failed in the history, okay? But for the critical state, or even we can use the peak parameter if this is an intact slope. Or we can say it's a fresh slope, just a cutoff slope, or just a fill slope, okay? We can use the peak value. But here, if we choose to use this conservative design parameters, you see the F value actually is smaller than 1, okay? And this one, actually, I will leave it to you for your own to study. Actually, we don't have the result here, the solution here, but we prefer to use this grid searching method, okay, to find out the result. And this one, this example, actually, we have already discussed. For the plain translational slip, we have example 4 and example 5 here. But for these two examples, actually, is relatively simple because we are just use the equation. Okay, this is for the water table exactly at the slope surface. Okay, similarly, we use this one. And if it is a dry slope, we assume the C prime is equal to 0. We just directly to use this equation for the dry condition, right? It's 2 times of this water table at the slope surface condition. If the water table is at 2 meter below the ground level, okay, 2 meter below the ground level, water table is here, this HW is equal to 2, okay? If this is the case, if we have the different depth condition for the soil ground, these depths we have different, okay? If the soil water table is 2 meter, HW is 2, and this Z again is equal to 2 meter, actually it's a dry slope case, right? All the yellow part of the ground is above the water table, right? Above water table. So if Z is equal to 3 or until to 6, okay? We just input different values for this Z, okay? Because we already have this equation. Okay, this is the same. If the water Z prime is here, Z is equal to 10 or even 50. Okay, you can see with the increase of the Z, the depth, with the increase of the depth, actually we can see the decrease of the factor of safety, right? So for stabilize one slope, actually we can, for example, this is angle here, the slope angle. We can do some layering, okay, layering or leveling, okay. To make this slope smaller, for example, we can fill up the slope. To make the slope, for example, fill up like this, like this, like this, okay? Then we can make this alpha value smaller. Or we can decrease the depth of this slope, okay, to decrease it. Okay, this is the second one. The first one to decrease alpha, the second one is decrease the Z, and the third one is try to increase the friction angle. Okay, try to increase this friction angle. How we can apply we can use some cement, okay, some kind of chemical agent to stabilize the slope. If you add the cement like this or lime to treat the slope, actually it can increase this phi. Then the F value will be increased. Okay. So this is 3 normally adopted method, okay, to stabilize the slope. Okay, so I will not go through the example 5. So I leave this example for you to go through by yourself. So this is all today, I mean, for the tutorial. So I will stop the recording now. Do you have any question about today's tutorial?